So, hey everyone, welcome back. We're at video 10. We've come a long way and are almost closer to finish the playlist. But today we are going to discuss something very important to understand in system design. Let's talk about why your app is slow. Not network slow, not bad query slow. I mean fundamentally, physically slow. Like slow in a way that no amount of refactoring is going to fix. Because here's the thing that most developers don't think about. When your CPU needs a piece of data, it doesn't just appear. That data has a physical home, and the distance between that home and the processor, that gap is the single most important factor in how fast your system actually runs. Today, we're going into the memory hierarchy. We're going to talk about caching, what it really is, why it works, and why it can absolutely destroy you if you get it wrong. We're covering the 90-10 rule, locality of reference, 3 caching strategies you need to know: cache aside, write through, and write back. And we're ending on what is genuinely one of the hardest problems in all of software engineering: cache invalidation. This is video 10. Let's get into it. I want to start with a mental model. Think of your computer's memory as a ladder. At the very top, you've got the CPU registers. These are tiny. We're talking a handful of bytes, but they are instant. The data is basically inside the processor. One step down, you've got the L1, L2, and L3 caches. These are small pools of ultra-fast memory that live right next to the CPU. Still incredibly fast. We're talking nanoseconds. Step down again, you've got main memory, RAM. This is your gigabytes. Fast, but you're starting to feel the distance. Down from there, the SSD. Slower, much slower. And at the very bottom, the spinning hard disk. And beyond that, the network, fetching something from a database in another data center. Now, those sound like generic descriptions, so let me make this real for you. Let me put these numbers on a human scale that actually lands. Imagine that one CPU clock cycle is 1 second of your life. Just 1 second. On that scale, accessing your L1 cache, the fastest memory, takes about half a second. It's like reaching for a pen in your hand, basically instant. L2 cache? About 7 seconds. You have to reach across your desk. Fine. L3 cache? About 25 seconds. You stand up, walk to the shelf, grab a book. Still manageable. RAM, main memory, that's about 2 minutes. In our analogy, you have to walk down the street to the library and wait for the librarian to find your book. 2 minutes. You notice it. Your whole train of thought is interrupted. Now, an SSD? On this same scale, reading from an SSD takes 4.5 hours. Let that sink in. You're trying to do math, and every single time you need to look up a number, you have to drive to another city, wait 4 hours, and come back. A spinning hard disk? That's anywhere from 2 to 5, emphasize months. 2 to 5 months for a single byte. And a network round trip to another data center, say 150 milliseconds, that's 2.5 years on our human scale. 2.5 years. The gap between L1 cache and a spinning disk is 7 orders of magnitude. That's not a performance difference. That's a different universe. And this is the problem that every large-scale system has to solve, because the data you need is almost never sitting in the L1 cache. It's down there on the disk, or it's across the network. So, what do?
We get a lucky break from the universe. It's called the 90-10 rule. Here's the observation. In almost every system ever built, 90% of all requests are for just 10% of the data. Think about Twitter for a second. There are billions of tweets stored in their databases. But what are people actually reading right now at this moment? It's the tweets from the last 10 minutes. It's posts from major accounts. It's whatever's trending. That is a tiny, tiny slice of the total data. The other 99.9% of tweets, they're cold. They're sitting on a disk somewhere and nobody is looking at them. Nobody has looked at them in months. This shows up everywhere. Your e-commerce site? Most page views are for the 20 best-selling products, not the 12,000 products in the catalog. Your video platform? The top 1% of videos probably accounts for 80% of your bandwidth. The universe, apparently, likes a power law. And this gives us a shot. If most requests are for a small subset of data, we can take that small subset, yank it out of the 5-month disk, and put it somewhere much, much closer to the CPU. This idea has a formal name, locality of reference, and there are 2 types you want to know. First, temporal locality. If a piece of data was accessed once, it's very likely to be accessed soon. The hot tweet example, the best-selling product. Data that was popular 5 seconds ago is probably still popular now. Second, spatial locality. If you access one piece of data, the stuff right next to it in memory is probably needed soon too. This is why when your operating system reads 1 byte from a file, it actually loads the entire 4 kilobyte page around it, because it knows you're probably going to need the neighbors. These 2 observations are the entire foundation of why caching works. We identify the hot 10%, we promote it up the memory ladder, and we keep it close. When the CPU goes looking for data, it checks the top of the ladder first. L1, miss. L2, miss. L3, miss. RAM, hit. Got it. In 2 minutes, not 5 months. If we can maintain a cache hit rate of, say, 95%, meaning 95 out of 100 requests find their data in the cache, then only 5% of requests ever touch the disk. The rest are answered fast. Your system feels fast. That is the only reason modern computing feels as responsive as it does. All right, but before we get to strategies, I want to be honest about the cost, because there is no free lunch here. RAM is expensive. Per gigabyte, it's roughly 10 to 50 times more expensive than an SSD. It's also volatile, which we covered back in video 5. If the power goes out, the cache is gone. Everything in it vanished. So when you add a cache, you are making a trade. You are spending more money on RAM, and you are accepting the risk of data inconsistency in exchange for speed. And here's the thing that makes caching genuinely hard. The moment you cache something, you've created a second copy of the truth. You've got the real data in the database, and you've got a snapshot of it in the cache. And the second those 2 diverge, which they will, you have a problem. There's a classic line in computer science from an engineer named Phil Carlton. He said, "There are only 2 hard things in computer science: cache invalidation and naming things." It's a joke, but it's not really a joke. We'll come back to invalidation at the end. For now, let's talk about the 3 main strategies. Strategy 1, cache aside, sometimes called lazy loading. This is the most common pattern you'll see in web development. And if you've ever used Redis with a Node or Django app, this is almost certainly what you're doing. Here's how it works. A request comes in for user 123. Your app checks the cache first. Hey Redis, do you have user 123? If the cache says yes, that's a cache hit. You get the data in a millisecond. Done. The database never even knew there was a request. If the cache says no, that's a cache miss. Now your app goes to the database, pulls the data, and before it returns it to the user, it writes a copy into the cache. So the next time someone asks for user 123, it'll be there. Simple, clean, and actually pretty resilient. If Redis goes down entirely, the app just falls back to the database. Slower, but it works. The cache is optional, not load-bearing. The downside? First request for any piece of data is always a miss. You pay the full price that one time. And then there's the consistency problem. What if user 123 changes their name in the database, but the old name is still in the cache? Now you're showing users stale data. Strategy 2, write through. Here, the cache isn't sitting beside the database, it's in front of it. Every single write goes through the cache first. Here's the flow. Your app wants to update user 123's name. It writes to the cache immediately writes to the database waits for the database to confirm, then, and only then, it tells the app. Success.
The big win here is consistency. The cache and the database are always in sync. There is no stale data problem. The cost? Writes are slow. Every write has to wait for the database. You've made reads fast, but you haven't made writes any faster. Okay, this is the interesting one. Strategy 3, write back. And this is how high-performance systems actually operate under the hood. In write back, the app writes to the cache, and the cache immediately says success without touching the database at all. The cache just marks the data as dirty, meaning I've got a version of this that hasn't been saved to disk yet. Then, every few seconds, or when the cache fills up, it flushes all those dirty writes to the database in one big batch. The performance here is extraordinary. Your write speed is limited by RAM, not disk. You can write millions of updates per second because you're not waiting for anything. But the risk is real. If the cache server crashes before it flushes, those writes are gone, permanently. The database never got them. You actually use this constantly without realizing it. When you save a document in Word and it says saved, the operating system has almost certainly just put it in the page cache, RAM, and told Word it's done. It might not hit the physical SSD for another 30 seconds. This is the entire reason you're supposed to safely eject your USB drive before you pull it out. You're giving the operating system a chance to finish the write back, to actually commit everything to the drive before you yank it. Write back is a bet. You're betting your cache server won't crash in the next few seconds. Most of the time it's the right bet, but you need to know that's the trade-off you're making.
All right, now we get to the hard part. Cache invalidation, the reason Phil Carlton's joke exists. The core problem: the truth has changed in the database, but the old version is still sitting in the cache. If you don't clear it out, your users see wrong data. Imagine you're building an e-commerce site. The cache says there's one Xbox left in stock. A user buys it. The database now says 0. But nobody told the cache, so the cache still says 1. Another user sees that 1 in stock, clicks buy, checkout fails. Or worse, you process the order and then have to call them and say, actually, we don't have it, we're really sorry. That's not a caching bug. That's a business failure. So how do we handle this? There are 3 main tools. Tool 1, TTL, time to live. Every cache entry gets an expiration timer. Keep this for 60 seconds. After that, throw it out. This is the blunt force approach. It's simple, it's predictable, and it works surprisingly well. But it means your data can be wrong for up to 60 seconds. For a social media feed, that's totally fine. Nobody cares if a tweet count is a few seconds stale. For a bank balance? No, not acceptable. You set your TTL based on how wrong you're allowed to be and for how long. That's a product decision as much as a technical one. Tool 2, eviction policies. What happens when the cache gets full? You have to evict something to make room. The most common policy is LRU, least recently used. Throw out whatever hasn't been accessed in the longest time. This lines up perfectly with temporal locality. If you haven't needed it lately, you probably don't need it. The other common one is LFU, least frequently used. Throw out whatever is accessed least often overall. LRU is the default for most systems because it's simple and it works. Redis uses it, most browser caches use it. Tool 3, manual invalidation. When your app updates the database, it also sends a delete command to the cache. Hey Redis, throw out user 123. The truth has changed. This sounds easy. In a small app with one server, it kind of is. But in a distributed system, it's a nightmare. What if the database update succeeds, but the network message to the cache is lost? Now the cache has the wrong version, and it'll stay wrong until it eventually expires. What if you have 10 cache servers and you only reach 6 of them? The other 4 are now permanently wrong. Every strategy has a failure mode. TTL means you're wrong for a window of time.
Manual invalidation means you're only as reliable as your network. Write through means you've traded write speed for consistency. There is no perfect answer. There's just the answer that fits your system's tolerance for staleness. Before we wrap up, there's one more failure mode you have to know about, because it's one of the most spectacular ways a cache can ruin your day: the thundering herd. Here's the scenario. You've got a database that can handle 1,000 queries per second. Your app is popular. You're getting 10,000 queries per second. But because your cache hit rate is 95%, only 500 of those queries actually reach the database. Everything is great. Now the cache server crashes. Suddenly, all 10,000 queries hit the database simultaneously. The database, rated for 1,000, now has 10,000 coming at it. CPU maxes out, disk queue explodes, database crashes. You restart it, the cache is still empty, it's cold. As soon as the database comes back online, the 10,000 queries hit it again. Crash. You're in a loop. Every time you restart the database, the empty cache lets the full load through, and the database falls over again. This is a real thing that has happened to real companies. Production down for hours because the cache went cold, and the database behind it couldn't survive the direct load. The fix is something called cache warming. Before you send real traffic to a server, you pre-populate the cache with the most common 10% of data. You build the shield before you open the gate. There's another failure mode worth mentioning: cache penetration. This is a deliberate attack. Someone sends requests for keys that don't exist. Get user 99 million, over and over. Every request misses the cache because there's nothing to cache. Every request hits the database. The cache offers zero protection. The solution? A Bloom filter. We touched on these back in video 5. Before a request even reaches the cache, the Bloom filter can tell you in nanoseconds whether a key might exist in your system. If it definitely doesn't exist, you reject the request immediately. Database never even gets the query. One more thing worth understanding: caching is not just one thing in your stack. It's everywhere. It's fractal. In your browser, your CSS and JavaScript files are cached locally. You don't download them every time you visit a site. At the network edge, CDNs, content delivery networks, are geographic caches. Netflix doesn't stream every video from a central data center in California. They put cache boxes inside your local ISP. When you stream a show in Amsterdam, you're probably getting it from a server a few kilometers away, not thousands of kilometers across the ocean. In your own infrastructure, Redis or Memcached sit next to your application servers and absorb the repeated database queries. Inside your database itself, Postgres and MySQL both maintain buffer pools, caches of the most recently read data, held in RAM to avoid hitting disk. And at the operating system level, the kernel keeps a page cache of recently accessed files in whatever RAM isn't being used for anything else. Your job as an architect is to look at the path of a single request and ask, where is the longest wait? If the user is in Sydney and the server is in New York, the bottleneck is the speed of light across the Pacific. A Redis cache in New York doesn't help. You need a CDN. If the user is in the same city as your server, but your queries take 2 seconds to run, the bottleneck is disk I/O. You need Redis. All right, let's land this. Caching is not a speed button. It's not just throw Redis in front of the database. It is a fundamental architectural decision to trade complexity and consistency for scale. If you've got a small app with 100 users, don't add a cache. Seriously, a single well-indexed Postgres instance on modern hardware can handle thousands of requests per second. The cache will just give you invalidation bugs with no upside. But once you hit the limits of a single machine, once your hot 10% is bigger than your RAM, once the 90-10 rule starts working against you, you have to start thinking in layers. Respect the latter. Know the difference between 2-minute RAM and 5-month disk. That gap is real, and it changes every decision. Trust the 90-10 rule. You don't need to cache everything. You need to cache the hot stuff. Cache that, and you've probably solved the problem. Plan for invalidation. If you're caching it, you need a plan for what happens when the truth changes. Protect the database. Your cache is a shield. Don't let the thundering herd through. Warm the cache before you send traffic. Know what lives behind the shield and how much it can take. Caching is the reason the internet feels instantaneous. It's how we make a CPU doing 3 billion things a second tolerate a disk that can only do a few hundred. It's the most powerful shortcut in software engineering. Use it carefully and always, always have a plan for when the lie gets stale. In video 11, we're going to shift gears completely. We've been talking about how to make requests faster. Now we're going to talk about how to make users stop waiting at all. Message queues, Kafka, asynchronous systems, the power of later. I'll see you there.